Good evening, good evening, everyone. So this is the NPTEL problem solving session for the course Robotics, Basics, and Selected Advanced Concepts. Um, so this is the problem solving session for week 6, and we'll wait for 5 more minutes for students to join. And if nobody joins, then we will just discuss some of the concepts that are very relevant to the assignments of week 6, and then we'll conclude this session. And if anybody joins in between, then we can also have any doubt clarification. So we'll wait for 5 minutes. So I think we should start. So this week's lectures are more related with link velocities, okay, like both linear and angular, okay, and as well as Jacobians, velocity Jacobians specifically, okay, and I saw that one of the question, is just a relation between your angular velocity and Euler angle rates, okay, the x, y, z Euler angle rates, and like some like both of these for both serial as well as parallel manipulators. Okay, so what we'll start with this, we'll start with a general discussion on the kinematics, okay, of rigid body, because as we discussed earlier, like a link is a rigid body, right? We'll just see how we calculate the velocity. Like we'll just go till velocity. Kinematics also includes acceleration and further terms, but we'll only discuss how we calculate the velocity of any rigid body. Okay, so let us say that we have a inertial frame, a ground frame, okay, that we call E naught. Okay, so this frame we call E naught, and let's say origin is O1, and the basis vectors are capital E1 hat, capital E2 hat, and capital E3 hat. Okay, and there is a rigid body, and that rigid body again we will you know represent the rigid body with a frame attached to the rigid body. Okay, so now this frame we will call E1, and basis vectors small e1 hat, small e2 hat, and small e3 hat, and origin O2. Okay, so well, first of all, most of the time all of the measurements are done in ground frame. Okay, because we have assumed that our ground frame is the inertial frame. Okay, why we do that? Because Newton's laws are applicable only in inertial frame. Okay, Newton's laws or Newton-Euler laws. Okay, so whatever quantities we have in any other frame or any quantity, we want to represent them in ground frame. Basically, how does that quantity look as seen from the ground frame? Okay, so let us rearrange things a bit. Okay, this is our E naught, E1. Okay, and like yeah, this is the position vector R. Like let us call the origin G. Okay, so this is vector R G O, right? Okay, as seen from O, and this is just a symbol of vector, yeah, the small underbar under R. Okay, and let us say that there is some point, P, right? So this vector is R P. G. Okay, so if we want to, study the dynamics of particle P, okay, so this particle P might be on the, body B itself. So, you know, this frame we discussed, it represents a rigid body. Okay, so this point P might be a part of the rigid body or might not be a part of the rigid body. If it is a part of the rigid body, then it moves with the rigid body. So there is no relative motion of P as seen from this frame E1. Okay, but right now we are just talking about a general case where P is, let's say, not a part of the rigid body. Okay, because if P is a part of the rigid body, then it becomes a special case. Okay, so as we said, we just want to know how everything looks like in inertial frame. Okay, so also similarly, we want to know that how does, like, what is the vector, like position vector of point P as seen from the origin of frame E naught. Okay, so what we want is actually RPO. Okay, and we know that this is R from vector addition GO plus RPG. Fine. So if I want to know the velocity vector, okay, of RPO, and this velocity also I want as seen in frame E naught. Okay, then simply like I just need to differentiate both of these vectors as seen from E naught. Okay, so now why I have shown this frame about which I want the rate of change, because the expression, like, it's different. Like, it matters in which frame you want to see the body moving, okay, or you want to express the, yeah, you are seeing the body moving. Okay, so let's say if there is a vector v, okay, and you are representing this vector v by, let's say, a matrix form, okay, in which this vector v is written in frame e1. Okay, so this velocity vector v, the comp, it is represented as seen from, frame e1. Okay, so it is still the same vector. Okay, like it can be any vector. Like if I do not take v, let me use some more generic, let us say some vector x. Okay, so the matrix form of x, so the components are as seen in frame e1. Okay, but if we want the velocity of x as seen in frame 0, okay, so how does this vector change, okay, when I am, you know looking at it from frame 0? So this actually gives me, like, this is related by what we call the transfer theorem. Okay, like let us say that I'm writing it as x in x1. Okay, so the matrix form, this represents this. Okay, plus, okay, so this is the extra term that comes in the transfer theorem. How is the frame in which the quantity has been expressed move with respect to the inertial frame, or the frame that you want to, measure the quantity in, times the vector x. Okay, so this is important to note. Okay, so what you can do is you can either represent everything in let's say the ground frame, okay, and then you can then this term will always be zero, right? Because it will be then omega of E naught with respect to E naught, right? So that will be zero. But if sometimes it is easier to represent some quantities in some different frames. For example, if you know I want to write the position of this point P, this vector rpg, okay, so this will be much easier, it will be much easier to represent this in frame E1 as compared to frame E0. Okay, so what we will do is, okay, we will just take a very quick example. Okay, and for our example, let us take our good old 2R manipulator. Okay, theta 1 and this is theta 2. And of course, we knew that this point of interest is the end effector for the 2R manipulator. So this becomes our point P, and our inertial frame or the ground frame we had attached here. Okay, this becomes here even E2. Okay, capital E and capital E to represent the ground frame. Let me just change the color. Hmm. Okay, and the first frame for the first rigid body. Okay, so this link 1, okay, was aligned like this: E1, E2. Okay, and let us say this second link, okay, is called E1. The frame attached to link 2 is called E prime. Okay, so this has E1 prime, E2 prime, and E3 prime as its basis vectors. So, what we do is we try to write the position vector of P as seen from O. Okay, let us say that this point is A. Okay, so again, this is R A with respect to O plus R of P with respect to A. Okay, and now you see R of A with respect to O. If I say that the lengths of this are L1 and L2, okay, so this is simply, L1 E1 plus L2 E1 prime, right? Now you see these quantities, these basis vectors, they are not in base frame, okay, like they're not in terms of capital E1 and capital E2, okay. So what I will have to do is, when I want to know the velocity of this point with respect to inertial frame, of course, we discussed, we just want to know everything in inertial frame, okay. So first we'll take this quantity, since this is expressed in frame E1 and this is like let's say E prime. Okay, so this is in E1 frame dy dt of L1 E1 plus omega of E1 with respect to E naught cross product with L1 E1, and then for the second term. Okay, E prime L2 E1 prime plus omega of E1 with respect to E naught, no, E prime with respect to E naught cross L2 E1 prime. Okay, now if you like see that since this vector, these vectors as seen from these respective frames, they won't change, right? Because this vector L1 E1 as seen from this E1 frame, it will not change even if the frame moves. Okay, if the E1 frame rotates, this vector will rotate with it. Okay, because the link will rotate with it. So this vector will stay same as seen from frame E1, right? So this quantity will be 0, and similarly for the same reasons, this quantity will also be 0. Okay, so what you we are left with is omega of E1 with respect to E naught cross L1 E1 plus omega of E prime with respect to E naught cross L2 E1 prime. Okay, so like we need to know the omegas beforehand, right? So what is omega of E1 with respect to E naught? Okay, now you see what is the relative angle between E1 and E1 and E naught. Okay, this is your E naught, this is E1. Okay, so this is theta 1 dot like E3. Okay, or I can even write it as theta 1 dot capital E3 because like both are parallel. And for E prime with respect to E naught, okay, what I will have to do is I will have to break this up into two different parts. Okay, E1 with respect to E naught. Okay, so now this term, okay, we know that the relative angle between frame E prime and E1 is theta 2, right? So this omega will be theta 2 dot, let's say E3 or E3 prime, whatever we want to call it, and this will be theta 1 dot same E1, right? No, E3. Okay, and you see for this particular problem, all the you know these Z axes or the E3 axes of all the frames, they are parallel. Okay, they are the same. Okay, so I can even write this one as taking E3 as common and then replacing E3 with E3 prime. Okay, now why I have done this, you will see in the next step. Okay, so let's say this was what? This was VPO, all right, velocity of point P with respect to. So what does this come out to be? VPO is theta 1 dot E3 cross product with L1 E1 plus theta 1 dot plus theta 2 dot E3 prime cross product with L2 E1 prime. Okay, so now you see in the cross product, I have all the cross product terms for the basis vectors of same frames. Okay, so I do not need to convert any one of the basis vectors into some other frame just to perform the cross product. Okay, otherwise, let's say if there was, just E3 in place of E3 prime, okay, then I would have to first convert this E3 into, its representation in E prime frame, or I would have to convert this E1 prime, into its representation in E1 frame. Okay, but for this particular problem, since all of these are same, okay, it makes our life easier. Okay, so this is L1 theta 1 dot, and what is E3 cross E1? E2 plus, like this is L2 theta 1 dot plus theta 1 dot, and this will be E2 prime. Okay, so now see, you have the velocity of point P in vector form. Okay, but still it is not in, you know, your basis vector. Like it is not in terms of your, you know, basis vectors of the ground frame. Okay, so now we'll work towards that. Okay, so we can clearly see that, the transformations that lead from one frame to the other is like from E naught we rotated about theta 1 to get, we can rotate about theta 1 to get E1, right? And then E1 can be rotated by theta 2, right? E1 is rotated by theta 2 to get E prime. Okay, so basically, if I write in terms of the basis vector, how the basis vectors are getting transformed, okay, I have some EIs, okay, and when I apply, let's say I call this R1 and this as R2. So when I apply R1, okay, so these get transformed into EI, right? And similarly, when I apply, yeah, that's- when I apply R2 to the small EIs, I get EI primes, right? Okay, and what is R1? Okay, so now if I write all these in matrix form, let's say I write the first one in matrix form, R1 and EI. Okay, so you see, whenever you write any vector equation into matrix form, all of the quantities should be, written in the same frame. So in this case, I'm writing all these in the E naught frame, and these quantities I'm writing in E1 frame. Okay, because otherwise you cannot compare, the matrices in two different that are represented in two different frames. That will be wrong. So this is even. Okay, and this also, represents that this equation, the first equation, will give you, expression of how is, let's say, E1 represented, okay, as a, you know, function or a linear combination of capital E's. Okay, so how does E1 or let's say EI look in terms of the capital EIs? Say, yeah, say J. Okay, so this writing that this in this equation EIs will be written in frame E naught is equivalent as, this saying that it represents this equation that EIs, it will be written in the form of, you know capital EIs. Okay, and also capital EI is written, what is, what is capital E, let's say, 1 as written in E naught frame. Okay, it is simply 100. Okay, what is small even as written in even frame? It is again 100. Okay, but what is small even written in E naught frame? Okay, so that is what this equation will give us. Okay, and for that we need the matrix form of R1, right? And from, like, you'll have to do your forward kinematics for this, but once you do that, you'll see that so R1 in E naught frame comes out to be, you know, cos theta 1 minus sine theta 1 and cos theta 1. So only the rotation matrix we are trying to write. Okay, right? And similarly, R2, okay, as written in E naught, it will be cos, let us write it as 1 2. Okay, like we will use the notation that sir was using in lectures. So this C1 S1 C1. Okay, so now let us come back. Let us just try to calculate what is E2 and what is E2 prime. Okay, so from the first equation, hello Peru Malay Swami, do you have any doubt? So what we are doing right now is just I am recording a lecture on the kinematics of general rigid bodies related to whatever the assignment problems you have in week 6, and then I'll upload it on a YouTube channel, the link for which will all might have already been shared with you guys. So other than that, if you have any doubt, then I think I can help you with that right now. Am I audible to you, Peru? Okay, well, I'll just go ahead with recording the lecture, and you can also follow it. And like, if you have any doubts during the lecture, then you can ask, or if you have any doubts in the assignments, you can ask that also. Okay, so okay, we first calculate how does E2 look in E naught. So that is R R1, okay, times E2 in E naught, okay, using the equation here. Okay, the first one of these two equations, relations, actually. Okay, and when we write them out, so they are C1 minus S1 0 0 1 S1 C1, and E2 as seen in frame E naught is 0 1 0. Okay, so this will turn out to be minus S1 C1 and 0, right? The second column of R1. Okay, now since this is written in frame E naught, what it actually means is that in vector notation, okay, E2 can be written as minus S1 times capital E1 plus C1 times capital E2. Okay. Now similarly for E2 prime, okay, that we need for the second term of velocity, okay, it will turn out to be minus S12 small e1 plus C12 small e2. Okay, and then when we replace these e1 and e2, okay, because we want to get everything in the ground frame, right? So this is c1 e1 plus s1 e2 plus c12 minus s1 e1 plus c1 e2. Okay, so this turns out to be minus c1 s12 minus s1 c12 e1 plus, or rather minus again, we can just write, you know, c1 c12 minus s1 s12 e2. Oh wait, this, since this is only r2 and r2 is only between e1 and e prime, okay, so it won't have 1 plus 2, right? Because the relative angle between 1 plus 2, or rather e1 and e prime, okay, it is only theta 2, as we saw above here. Okay, so it will only have theta 2 values, r, this will be s2. Okay, and so this right here will have only s2. Okay, s2 c12 c2 s2. Okay, so e2 prime, now combining these, using the trigonometric identities, what we get is c12 e2, because you see c1 c2 minus s1 s2 is, c12 cos ab minus sine cos a cos b minus sine a sine b is cos a plus b. Okay, so this is cos theta 1 plus theta 2, the first term, and the second term is minus, right, minus s1 to e1. Okay, so now we have our e2 and e2 prime, as seen in base frame, okay, or in terms of the basis vectors of the base frame or the ground frame. Okay, so we'll just substitute them in our velocity relation that we got. Okay, so what it came out to be was L1 theta 1 dot E2, right? L1 theta 1 dot minus S1 E1 plus C1 E2, and then plus L2 theta 1 dot plus theta 2 dot E2 prime. Okay, so C12 E2 minus S12 E1. Okay, so now let us just collect, E1 and E2 terms from both these equations. It will be minus L1 S1 theta 1 dot and plus L2 S12. So this will not be plus, so minus theta 1 dot plus theta 2 dot E1 plus L1 C1 theta 1 dot plus L2 C12 theta 1 dot plus theta 2 dot E2. Okay, now just let's say rearrange further within the brackets. We combine terms of theta 1 dot and theta 2 dot together. Okay, what we will get is minus L1 S1 minus L2 S12 theta 1 dot minus L2 S12 theta 2 dot E1 plus L1 C1 plus L2 C12 theta 1 dot plus L2 C12 theta 2 dot E2. Right, this is your velocity expressed in terms of the basis vectors of the ground frame. Okay, so the ground frame. Okay, so now if we write it in the matrix form, okay, the same vector. Okay, so these components are in ground frame, right? So it will directly be minus L1 S1 minus. So we are just writing the components of E1 and E2 here, right? Theta 1 dot minus L2 S12 theta 2 dot and L1 C1 plus L2 C12 theta 1 dot plus L2 C12 theta 2 dot, and like the third one is 0, right? There is no motion in Z axis in this case, or along the E3 axis. Okay, so now if I look at it, okay, so this is actually the x dot and y dot. Okay, and in vector form it is the x vector dot, right? Okay, and if I look carefully, the only this x dot and y dot if I write, okay, so it will just be the first two you know equations, right? L2 S1, I'll just write it out quickly. L2 S1 theta 2 dot L1 C1 L2 C12. Okay, so if you take a good look at these equations, so they are linear in theta 1 and theta 2, right? So since they are linear in theta 1 and theta 2, I can write it in the linear matrix form, right? Where, I just decompose this, 2 cross 1 vector into a matrix multiplication of a 2 cross 2 matrix with a 2 cross 1 vector, right? L2 S12 minus L2 S12. Yes. So these are the coefficients of theta 1 and theta 2 respectively that were there in the equation. And this multiplied by theta 1 dot and theta 2 dot. Okay, this is your x dot and y dot, right? So now you must have seen this particular form in lectures. Okay, and we also write this as x dot equal to j theta dot. Okay, so this matrix here, okay, is what we call the Jacobian matrix. Okay, so this is called the Jacobian matrix. Okay, so like this is some very nice properties. If you see, it is telling me that for any given theta 1 dot and theta 2 dot, it means for if I am rotating my joints at some rates. Okay, where is the figure? Yeah, so if I am rotating these joints, right? I have two joints in this system, that's why it's called a 2R manipulator. If I rotate these at some given rates, okay, what will be the velocity of the end effector? Okay, so you already had something like this, right? X equal to the forward kinematics mapping. Okay, now when you differentiated this, now if when you, what you got from the forward kinematics, if you differentiate it, you'll get the same result. Okay, like we just have taken a different approach to calculate, let's say, like the position part of the forward kinematics. Okay, like this is just a different approach of calculating the position of the end effector. Okay, as compared to the transformation matrices that we have seen earlier. Okay, so now you see you have the relation between both the angular position, end effector position, angular rates, and end effector rates. Okay, so but similar to what we did with the forward kinematics, okay, what we did was we defined an inverse kinematic solution. Okay, that for any given x vector, we wanted to calculate theta. Okay, so similarly, okay, because if we want our you know end effector to move at a particular velocity, okay, if we know that the end effector should move let's say in the horizontal direction towards the right with a velocity of 1 meter per second. Okay, then this is the relation that we can use, right? We are directly inverting this equation. Okay, but now you see there is a problem. Okay, like what problem? But there is not a problem, there is a catch. Okay, so this J, the inverse of this matrix J, it does not always exist. Okay, and okay, like another way of saying this is determinant of J equal to 0 for some cases, right? Some cases. Now you see this J right here, it's a function of theta 1 and theta 2, right? Okay, so we can just write it in the functional form, theta 1 and theta 2, like inverse x dot. Okay, so we are saying that J is not always, you know, like J inverse does not exist. Okay, determinant of J is, non-zero, not always. Okay, so it means that there are some configurations. Okay, my configurations, because my configuration is defined by theta 1 and theta 2, and since J only depends on theta 1 and theta 2, okay, physically it means that there is some configuration of my 2R manipulator at which J becomes singular. Okay, singular means the determinant is 0. Some configurations, and it is not true for all configurations. Okay, these are some special configurations. Okay, so configuration is just a set of your theta 1 and theta 2, any pair of values, like some pair of values for like all these three statements that I've written, they mean the same. J is singular. Okay, and what is the example of like what does it mean physically. Okay, it means that if let's say the robot is the first link is like this, okay, and the second arm, if it is like this, okay, then what happens is like what are the possible directions in which this arm can move? Okay, instantaneous directions. Okay, so right now in this configuration, okay, where you have some finite theta 1 and a finite theta 2, okay, so this robot can actually move in all the directions, right? Basically it can have any finite velocity, not any, some finite velocity in both the directions, so it can move like in the 2D plane, right? It is not constrained to move in any particular direction. But if the condition is like this, that the second link and the first link, like they have lined up like this, okay, now you see the instantaneous, like the robot cannot move along this direction, right? The robot cannot move along this red direction. Okay, it is not possible because now it will have to break apart to move in that particular direction. Okay, so in this case, the velocity or the motion direction for this particular robot has been constrained in this direction, right? It can only move in this direction for this particular configuration at this instant. Okay, like it just cannot move in this direction. Okay, so this particular configuration, okay, like this is what we call a singular configuration, where where we have a loss of degree of freedom. Okay, and for a 2R manipulator, okay, we know how to calculate this, right? You just calculate determinant of the matrix J. Okay, this is the matrix J, this is J matrix. You put it to 0, okay, and then you know you'll get a singular configurations. Okay, so if you try to calculate it, like you can try to calculate, you'll see now physically we can say that, see that this particular solution is when theta 2 equal to 0, and this will also happen when this link 2 is on the other side, right? So basically when theta 2 equal to pi, right? Now you can write n pi, you know, but this actually like gets a point through. Okay, so this is a singular configurations for your 2R manipulator. Okay, so like this is um, what essentially is the concept that we are trying to know. Now you see this mapping right here, right? We have discussed earlier that this is a mapping from input to output, right? The forward kinematics mapping. And I'm saying that this velocity relation is just a derivative of the forward kinematics, right? So it means this relation will also be, a relation between inputs and outputs, right? Input is theta 1 and theta 2 in this case. Okay, it means the actuated variables, okay, or the independent variables and the desired end effector variables. Okay, so this mapping is also between the actuated variables and the desired end effector variables. Okay, so like I'm just give you a small intuition. Okay, you had a parallel manipulator in one of your assignments, a 5-bar mechanism, right? Okay, so in this mechanism, we had told we were told that theta 1 and theta 2 are the actuated variables, right? And these were the inputs of the system. Okay, just giving theta 1 and theta 2 defined the whole configuration of the robot. Okay, so and let's say that this is the end effector that we have defined. Okay, so in this particular case, you know, you will get some, something like a similar relation, not the same, but a relation of the similar form. Okay, so this is not explained. Dots. Okay, when you try to get the velocity relations. Okay, but for a 4-bar mechanism, even if there are 4 different links, we know that there is only one actuated variable. Okay, so like in this particular case, when you wanted to write x, okay, it will only be dependent on, it will depend on both theta and theta 2. But in this particular case, let's say this is x and y, the vector x. Okay, this is scalar x, y. Okay, so this is a, now in this case it is only a function of theta 1, right? So when you try to get the velocity relation, okay, so this will be a Jacobian, and then there will be only the actuated variable rate. Okay, this is like important. So this, you know, dimension of your input and dimension of your output will decide the size of your Jacobian. Okay, so in this case it is 2 cross 2. Okay, but in this particular case, since there is only one variable here, so it will be 2 cross 1. Okay, so just keep in mind your actuated or the input variables and the desired or the output variables, right? Now there is just one more thing that I will discuss, relation between our angular velocity and Euler angle rates. Okay, so you have already been given one relation between angular velocity and components of the angular velocity in ground frame and Euler angle rates in the subjective assignment, and you have been asked for essentially the inverse mapping. Okay, but what I will discuss here is how we get those relations. Okay, so like for this we'll just take a quick look at how do how does the Euler XYZ parameterization work. Okay, so like we'll use the notation that we have used till now. There is a base frame E node. Okay, and then there is a rotation about x-axis by, let's say, angle phi. Okay, and let us not call it phi. Okay, we'll just call it theta 1. Okay, we'll keep it simple. We just theta 1, and so this E1, and so rotating E node by theta 1 with respect, about x-axis gives us E1. Okay, and rotating E1 about the y-axis of E1. Okay, not the original y-axis, by theta 2 it gives us E2. Okay, and rotating E2 about, z-axis of E2. Okay, so each of these frames, E0, E1, E2, they all of them will have 3 basis vectors, right? So if we just call them x, y, and z for each respective frame, then this is y is for this respective E1, this x is for this respective E0, and this z is for this respective E2. Okay, we rotate it by theta 3, we get E. right? So, you know, what we are interested in finding is, so this E is actually, the body frame, okay, or the frame that we were interested in, right? That is why we are talking about the angular velocity of the body. Okay, so how do we write the angular velocity actually? Like we want E with respect to E naught, right? We want everything with respect to the ground frame. Okay, so again, since there are three intermediate frames, okay, so I can break this down. E2 plus omega E2 with respect to, as seen, with respect to E1, and omega of E1 with respect to E naught. Okay, now you see, for E1 and E naught, the only relative displacement was theta 1, right? About x-axis. Okay, let us call the x-axis of E1 as capital E1. Okay, let us call the y-axis of the x-axis of E0 as capital E1, y-axis of E1, the next frame, as small e2. Okay, and the z-axis of the further next frame E2 as small e3 prime. Okay, so the only rotation between E1 and E naught is the rotation about the E1 axis by theta 1 angle, right? Theta 1 is the angle that is changing. So the rate of change, the angular rate of change between both of these frames will be theta 1 dot about E1 axis, right? And for this E2 and E1, it is only theta 2 about the y-axis of E1, that is your E2. And lastly, theta 3 dot for E3 prime, right? Now, as again, these quantities, we want them to be expressed in the ground frame, like with respect to the ground frame. Okay, so we write again our basis vector relations. Okay, so what is EI hat? They are R1. Okay, so we'll call this R1. This is R2, the transformation, and this is R3, the rotation, actually, not the complete transformation. Okay, and this is capital EI, right? And for EI prime, okay, it will be R1 right multiply R2, right? Because these are Euler rotations. So all these rotations are successive. Okay. So the next rotation is respect to the new axis. The further next rotation is respect to the latest axis. Okay. So that is why we right multiply. If all the rotations were with respect to the original axis, then we would have left multiplying. Okay, like let us not just jump the gun. Okay, otherwise we could have written like directly, this EI here, right? Let me just show you that relation as well. Okay, we are saying that EI is R1 and capital EI, and EI prime is, R2 small ei, and replacing small ei from the above equation, it becomes R2 R1 capital EI. Okay, but these are just tensor equations, right? I've not written them in matrix form yet, and I told you that when we are writing them in matrix form, then all the quantities, okay, like this, if I am talking about the second equation, this EI prime, R2, R1, they should all be represented in the same frame. Okay, let's say if I directly write it in the E naught frame, okay, then this has to be R2 in E naught frame times R1 in E naught frame and even hat, like EI hat in E naught frame. Okay, now what is, you know, like what is the matrix form of R1? Okay, like we only know R1 in E naught frame, right? All these rotation matrix that we write is with respect to the frame, the initial frame actually. Okay, so R1 is your C1 minus S1, S1 C1 0 0 and 1. Okay, now when we are talking about R2, okay, if you say that, you know, this R2, like since it is Y, if I write C1 S1 0 1, so these are all the fundamental rotation matrices. Okay, like you guys might know this. C2. Okay, so this form is only, you know, it is as seen from frame E1, not E0. Okay, if you want to you know, write this R2 in frame E0, you need to convert this quantity. Okay, and after conversion, okay, I'm not showing you how that conversion is done. Okay, it is like essentially the tensor transformation, just R2 in E1, you know, and since E1 to E0 the mapping is given by R1, so this is R1 E0 and R1 E0 transpose. Okay, so like this is your R2 in E0 frame. Okay, like you can also try to derive it. It is like, I won't say straightforward, but not too difficult. Okay, so in your matrix form, okay, so this comes out to be R1 E0, R2 E1 and capital EI E0. Okay, so what we actually need is E2 and E3 prime, right? And let us just write R1 times R2, right? The matrix form of R1 E0 times R2. Okay, so this is, hmm. So I think, oh no, yeah, they are about different axes, right? This is C2 0, no, plus S2 1 0 0 minus S2 0 C2. Okay, so what it results in is C1 C2 minus S1 and C1 S2 and then S1 C2 C1 and S1 S2 in the last row will be minus S2 0 and C2. Okay, so this is, you know, the multiplication of both of these. Okay, so now What actually did we need? We needed E2 and E3 prime. Okay, so E2 is like, we already know what, you know that is. Let's write in the matrix form itself. Okay, in E naught frame it will be, you know just minus S1 C1 0. Okay, and E3 prime in E naught frame, using this equation, just multiplying this by 0, 0, 1, that is, your E3. Okay, you'll get the third column essentially. Okay, so this will be C1 S2 S1 S2 and C2. Okay, so like writing this in vector form again, just for putting it back in the equation above. C1 E2 and E3 prime is C1 S2 E1 plus S1 S2 E2 plus C2 E3. Okay, so now, okay, so this equation will just replace, put those values. So omega of E with respect to E naught is theta 1 dot E1, right, plus theta 2 dot small e2, and the small e2 is minus S1 E1 plus C1 E2 plus theta 3 dot E3 prime C1 S2 E1 plus S1 S2 E2 plus C2 E3. Right? Oh, so wait, I think we might have done a mistake. So this first rotation is about X, right? So like we wrote the rotation matrix for rotation about Z. Okay, so this will be 1, 0, 0, C1 minus S1, S1 and C1, right? So again, here it will be 1, 0, 0, C1, S1, 0, minus C1, 0 minus S1 and C1. Okay, so the product also, yeah, gets updated. So this will be your C2, and then 0, 0. Second row will be S1, S2 and C1 minus S1, C2, and S2. And the third row minus C1 S2 S1 and C1 C2. Okay, so now writing these correctly, they will be 0 C1 S1 and this E3 prime will be the third column of the corrected R1 R2. This will be S2 minus S1 C2 C1 C2. Okay, writing them in the correct vector form. So this will be C1 E2 plus this is just C1 S1 E3 and this is S2 E1 minus S1 C2 plus C1 C2. Okay, and once we update this here as well, C1 E2 plus S1 E3 S2 E1 minus S1 C2 E2 plus C1 C2 E3. So this comes out to be, just combining all the E1, E2 and E3 terms plus theta 3 dot S2 E1 plus theta 2 dot C1 minus theta 3 dot S1 C2 E2 plus theta 2 dot S1 plus theta 3 dot C1 C2 E3. Okay, and if we just want to write this in, so this is omega of E with respect to E node as seen in, okay, base frame. Okay, here also as seen in E node frame. So in matrix form it will be written like this plus theta dot S2 theta 2 dot C1 minus theta 3 dot S1 C2 and theta 2 dot S1 plus. So this is basically how you can get the expression for angular velocity and expressing the components of angular velocity in base frame. Okay, so components of angular velocity as in base frame. Now what you've been asked is, you have been asked like this is of like this, right? It is a how should we write? Okay, it is a function of theta 1 dot, theta 2 dot and theta 3 dot. Okay, basically if I can also say this is a function of the vector theta dot. Okay, and what you have been asked is the inverse mapping. Okay, so you want in terms of these components of omega, right? Omega x, omega y, omega z, or whatever you want to call it, omega 1, omega 2 and omega 3. Okay, and this inverse mapping will be much easier to calculate if you just you know look at this equation. You will realize that this equation, okay, or basically this vector, like all these equations are linear in theta dots. Theta dots. Okay, so you can just break this in a matrix vector form and then just invert the matrix to get the required relation. So I think this will be enough for you to, just get on with the assignment. And as always, if you have any doubts, you can put on the forums. And I think I'll end the meeting here. So, uh, so yeah, thank you.